To understand chemostratigraphy, we need to know a few things of chemistry. Let's consider an isotope exchange. AA1 plus BB2 equal to AA2 plus BB1. Note this A and A are the same, and this small b and that small b are the same. In an isotopic exchange, there is no net reaction, but only the isotopes distribute between different chemical substances, and I will show soon an example. To compare this with a real example, consider this equation. We are going to define the fractionation factor or the equilibrium fractionation factor. It is defined on chemical equilibrium reactions where there is no net reaction, as I told earlier, but an exchange of isotopes which affects the equilibrium constant. This equilibrium constant K we are going to define for this equation. Does it have any geological significance? Yes, it has a significance. Forams can secrete their calcite shells, CaCO3, and in ambient sea water this reaction can take place. So, this reaction can happen on the forams tests. Let me write the general equation AA1 plus BB2 equal to AA2 plus BB1. So, here comparing between these two, small a is equal to 1, small b equal to 1/3, and a and b remain the same, they do not change. Here 1 has come over here and 1/3 has come over there. Now, we can define the equilibrium constant K in this way: A2 divided by A1 to the power A, B2 divided by B1 to the power B. Let me write down here in the next page. So, if I do that for this equation, K equal to Ca C 18O3 to the power 1/3 H2 16O divided by Ca C16O3 to the power 1/3 H2 18O. These superscripts A and B can be remembered. This A was associated with A1 and A2, and this small b was associated with B1 and B2 if we look at this reaction. Small a was associated with A2, small a was associated with A1, small b was associated with B2, small b was associated with B1. So, in this way it has been written. Since a is equal to 1, so this would be to the power 1, and here also to the power 1, and since b was 1/3, we have written 1/3 in these places. Now, this K can be written in a little bit different way. We can write this one, and then to the power 1/3, and then the H2O portion, which can be written in the denominator in this way. In this equation, we have said that A and B contain either the light or the heavy isotopes 1 and 2 respectively. Here, we are dealing with isotopes 18O, 16O, where the 16O is the lighter one and 18O is the heavier one. And in this reaction, only isotopes of a single element oxygen is considered. We are not considering more than one isotope getting exchanged. The terms inside the parenthesis, that means B2 divided by B1 and A2 divided by A1, are the molar ratios of these species. So, in this case, the terms inside the brackets actually represent the molar ratios. So, what we have obtained in terms of language, equilibrium constant capital K can be expressed as the ratio of 18O by 16O in the carbonates. Here is the carbonate, here is the carbonate, to that in the water. This is that in the water. Now, from here, from the equilibrium constant, we can move one step ahead and can define another very important parameter, the isotopic fractionation factor alpha. Since in this reaction we are having CaCO3 and H2O alpha and as subscript CaCO3 dash H2O, it can be stated as 18O by 16O found in CaCO3 divided by 18O by 16O found within H2O. In this way, the isotopic fractionation factor alpha, simply it can be written as alpha, is defined. In terms of language, it is a ratio of isotopes in one phase to the other coexisting phase. Now, a relation exists between alpha and K. Alpha is equal to K to the power 1 by n, where n is the number of atoms exchanged. So, we have to remember these equations, equation 1 and 2, this is equation 3 and this is equation 4. This alpha magnitude or the alpha CaCO3 dash H2O at 25 degree centigrade is found out to be 1.031. After the isotopic fractionation factor has been defined, let us look at another term, separation factor, which is given by epsilon equal to alpha minus 1, and epsilon multiplied by 1000 approximates the fractionation in parts per thousand, because it has been multiplied by 1000. What was written here, alpha, in this way the general symbolic presentation can be alpha A dash B equal to R A divided by R B. What is R A? From this equation, taking that example, R A is equal to 18O by 16O for CaCO3 and R B is equal to 18O by 16O for H2O. This is the note for the beginners, that here we are dealing with 18O by 16O for CaCO3 and the same ratio from water. You cannot have alpha equal to 18O by 16O for a mineral A and then 16O by 18O for a compound B. That way is not possible. If the ratio is 18O by 16O in the denominator also, it has to be 18O by 16O. A delta value in the isotope geochemistry, how it is defined? For the two compounds A and B whose isotopic compositions have been measured in the laboratory by conventional mass spectrometry, delta A is equal to R A divided by R standard minus 1 multiplied by 10 cube, and delta B is equal to R B divided by R standard minus 1 multiplied by 10 cube. Here R A and R B are the respective isotope ratio measurements and R S T is the isotope ratio of a standard sample. We are going to see in the next slide more detail about the standard sample. When we defined R A and R B and use in these formulas to define delta A and delta B, note that R A and R B are the ratios of the abundance of the less abundant or the heavier isotope to more abundant lighter isotope. The lighter isotope is more abundant and the heavier isotope is less abundant. For example, the R oxygen will be equal to 18O divided by 16O, because 18O is heavier and is less abundant and 16O is more abundant and is lighter one. Further to explain, Ra can be stated as the heavier isotope by the lighter isotope ratio of a sample. Similarly, Rb is represented as heavier isotope by the lighter isotope ratio for some sample, and the R standard is equal to the heavier by the lighter isotope, same isotopes in a standard sample. Since we are doing ratioing and then we are dividing the two ratios, naturally delta values are dimensionless quantity, and always we keep the heavier isotope in the numerator. You see, it is H divided by L, not L divided by H. H is always in the numerator, lighter one in the denominator, and a positive delta value will mean that the sample is comprising of more number of heavier isotopes than the standard value. And instead of multiplying by 10 cube as is done here, if I multiply it by 10 to the power 4, then naturally instead of parts per 1000 ppt, we have to write parts per pptt, that means parts per 10,000. ppt and pptt are definitely different. Let us see how do we write delta A. It is equal to Ra divided by R standard minus 1 multiplied by 1000, which is equal to Ra minus R standard divided by R standard multiplied by 1000. Now compare this expression with this expression, with this expression and with that expression. D by H SMO is the R standard in this case of delta D, and 18O by 16O SMO is the R standard in this case. Delta D, this is the symbol of parts per 1000, this is percentage, and if I multiply with 1000, this is the ppt symbol, parts per 1000. So back here delta D is D by H, the heavy isotope of hydrogen and the lighter isotope of hydrogen in the sample, minus that in the SMO. SMO means standard, I am going to tell, and divide by D divided by H found in the SMO. Most meteoric waters have got negative del 18O and delta D value. Delta D means the delta deuterium isotope of hydrogen. The evaporation fractionates the lighter isotopes and create negative values for H2O in the atmosphere. This I have already said. Now, because it is generally well mixed, deep ocean water mostly have delta 18O nearly same as the delta D, which is nearly equal to 0. We will see more detail in the next slide. Surface waters may deviate significantly due to evaporation and dilution by rain waters. So, the surface water, the sea water and the atmospheric water will vary in the delta values for oxygen and hydrogen. So, in this slide, delta, this symbol has been defined. Recollect the alpha symbol obtained from here. Let us take this reaction and find out how far this relationship is true. Consider the delta value, delta A and delta B, alpha value and 10 cube log of alpha A dash B. I take the delta A value such as this, delta B value like this. Now, delta A dash B is equal to delta A minus delta B. So, 1 minus 0 is equal to 1, 5 minus 0 equal to 5, and in this way you go down, 30 minus 10 is equal to 20. Now, from experimental means alpha A dash B has also been obtained. This is now multiplied by 10 cube and then this table is produced. Now, we want to compare delta A dash B and this table values. Here it is 1 and there it is 1, there is a perfect match. Here it is 5 and it is 4.99, 5 is nearly equal to 4.99, and in this way as you go down, here it is 20 and here it is 19.61, 19.61 is nearly equal to 20. That is why it is stated here delta A minus delta B is nearly equal to 10 cube log alpha A dash B. We have not given equal to symbol. As this difference increases, delta A minus delta B value, its difference from 10 cube ln A dash B also increases. For example, when delta A minus delta B was small, such as 1.001, it is almost same as 10 cube ln alpha, and when delta A minus B is equal to 20, a big number, then we do find some difference between delta A minus B and 10 cube ln alpha A dash B. We were talking about the isotopic standards. We are going to see now in little bit detail. The standard water sample, this water should be sufficiently stable, homogeneous, widely available, and that isotopic ratio should be near the mean of the natural variations. Now, if such water is created in the laboratory by someone, that is called as the lab standard or the working standard. The primary reference materials, which is the international standard for a few of the light elements, are the Vienna standard mean ocean water given by VS MOW for del 18O and del 2H. Vienna PD belemnites VPDB. Belemnites is a fossil for del 18O and del 13C, and for air nitrogen for del 15N. Vienna Canyon Diablo troilite and iron meteorite for del 34S, etc. What is important for us are the VSMO and the VPDB. At least these two should be remembered. Now, the laboratory generated standard VSMO was distributed in different labs for the geochemical studies. There are two international standards, PDB and SMO. These are of historical importance in the development of application of stable isotope techniques for the climate related studies. What is SMO? Standard mean ocean water. It is a hypothetical standard with del 18O value close to the modern mean seawater values. The value of SMO was defined by Craig with respect to an existing water standard NBS 1. SMO right now does not actually exist as a real water sample, so it cannot be used for calibration in the laboratory measurements. Therefore, a water sample with values identical of SMO was distributed by a lab, and that is called the VSMO, where V stands for Vienna, the city where the organization IAEA is established. Now, here onward is the detail the student can go through if interested. The PDB standard is used in the low temperature carbonate studies. The original PDB standard was a carbonate obtained from fossilized rostrum cigar-shaped internal shell of belemnite, which is an extinct cephalopod from the PD formation, and this PD formation is of the Cretaceous period in South Carolina, USA. Again, PDB standard over the years has been exhausted and it does not exist anymore. To overcome the problem, IAEA introduced the hypothetical standard VPDB with almost identical PDB. The relation between VPDB and VSMO is given by this equation for delta 18O, and it can also be written in this format. Delta I have already defined. There is another kind of delta given by the triangular symbol, and it has been used in this way: delta 17O, delta 25 mg and delta 33s. Different definitions of delta exist. Delta 17O is equal to this previous delta symbol 17O minus lambda delta 18O. So, here while defining the delta of the isotope, we are taking the lighter isotope. So, in case of oxygen it is 17O, and then we write is equal to delta, the previous symbol of delta, and this lighter isotope again comes here minus lambda, then delta, then we are putting the heavier isotope. 18O is a heavier isotope. So, here comes the 18O. Similar principle will work here. Delta 25 mg, 25 mg is the lighter isotope. It is equal to delta 25 mg minus lambda delta 26 mg. So, 26 mg is the heavier isotope. Similarly, delta 33s, 33s is the lighter isotope, is equal to delta 33s minus lambda delta 34s, where 34s is the heavier isotope of S. In all these cases, lambda is a parameter that characterizes the mass dependent fractionation. We need to understand in the context of chemostratigraphy what is time averaging and what is the compositional averaging. The geochemical data from the same bed, that means from the same horizon, ideally should represent variation in time and mixing of geochemical signatures of different environments. Consider this is a place of deposition, and contemporaneously from two sources grains G1 and G2 have come. On this surface we are having different grains and they can be of different ages. So, in this way variation in time can be explained. If the G1 and G2 are analyzed for geochemical data, then we can get mixing of geochemical signatures of different environments. The GSSP of the Eocene base, that means the base of Eocene, is a prominent carbonate isotope excursion, a spike in the carbon values, and the carbon isotope data comes from shell of forams and from the calcareous nanofossils. Now, these fossils can be of different ages coming from different sources. Secondly, consider this is a soft sandy bottom and a burrowing organism starts digging and then throwing these materials up on the surface. So, materials of two time horizons T1 and T2 get mixed up. This is meant by stratigraphic disorder due to bioturbation. The common example is crabs and where they act in the tidal flats. Consider we are taking two samples of foram of same species. It may be possible that the first appearance and the last appearance are diachronous even in this case. So, a combination of stratigraphic disorder and the diachronity in the evolutionary FA and LA will make any geochemical information such as the carbon isotope excursion CIE in the Eocene base questionable, in the sense that this data was prevalent for what time span remains a question. So, in this way the carbon isotope excursion on the Eocene base, which one is questionable? The chemical data seemingly correct, but is it really of Eocene base? That becomes the question. Due to the stratigraphic disorder, time averaging of fossil assemblages happen. We may not get the accurate time when the specific chemical data was prevalent. Note that different shells on bedding planes, shells of microorganisms of geologically older strata may differ in age by hundreds or thousands of years. So, consider this is the base on which we are getting two samples S1 and S2. Then the age difference between S1 and S2 can be hundreds or thousands of years. somewhere in the world, time averaging in forams in beach sand can be as high as 2000 years, and a resolution finer than 1 to 2 million year can be difficult to achieve when chemostratigraphic data are interpreted. What are the different magnitudes of time averaging in different types of fossil assemblages? In case of a coastal region, the variation can be 1 year to 1000 years. In the shelves, it can be more than 10 years up to 10 kilo years. In the coastal area, it can be say 90 years up to 90 or 80 kilo years, and similar age ranges exist for the shelves. One more problem of geochemical analysis of the calcareous test can be explained through this figure. A modern foraminifer is shown in this figure. Different portions of the shell have different del 18O values. For example, if analysis has been done from the center towards the periphery, this kind of pattern is noted. That means the highest value of del 18O at the center, then the value keeps falling steadily, attains a minimum value, then the value again keeps on increasing and attains a high value, but this value you can see is less than that value, and then again it falls. So, different portions of the shell can have different histories. If we get a single value of del 18O, that becomes an averaged out value. These are the problems in using chemostratigraphy on the fossil samples. Depending on which part of the shell is analyzed, the difference in isotopic value may be of the order of around 2.5 parts per mil.